Welcome to the deep dive. Today we're diving into a really special collection of mathematical ideas. We've got sources centered around this unique concept from the legendary mathematician Paul Erdős.
That's right. Erdős had this beautiful, almost mystical idea about the book.
The book.
Yeah, like a divine ledger somewhere, holding the most perfect, the most elegant proofs for mathematical theorems. Proofs so clear, so insightful, they just feel right.
Like they couldn't be any other way.
Mm-hmm.
And the book we're looking at today, Proofs from the Book by Aigner and Ziegler, it's basically a human attempt to guess what's in that divine book.
Exactly. It's trying to capture some of those perfect proofs, and it's clearly resonated. It's been translated into, dozens of languages.
It really has. Shows how much people value that kind of mathematical beauty, I think.
Totally. It's about finding beauty in pure logic and structure.
So our mission for this deep dive is to unpack some of these proofs. We want to figure out what makes them feel so, book-worthy. What's that special insight?
Right. What elevates them from just being correct to being, perfect?
Okay, let's jump in. We've got stuff from number theory, geometry, combinatorics. It's a real mix.
A whole journey through different mathematical landscapes, often surprisingly connected.
Absolutely. Let's start with something foundational. The infinity of primes. Now, most people know Euclid's proof.
Right.
Assume there's a finite number, multiply them, add one, contradiction. Classic. Beautiful.
It is beautiful, but the book, our source here, highlights a different approach. A second proof using Fermat numbers.
Ah, yes, Fermat numbers. Fn equals 2 to the power of 2 to the n plus 1. So S0 is 3, F1 is 5, F2 is 17.
Yeah.
They get huge really fast.
Incredibly fast. And the core idea here, this clever bit, is to prove that any two different Fermat numbers are relatively prime.
Relatively prime, meaning they don't share any common factors other than 1.
Exactly.
Okay, wait. Why does that show there are infinitely many primes?
Well, think about it. If you have an infinite sequence of numbers, F0, F1, F2, and so on, and no two of them share a prime factor,
then each one must contribute at least one new prime factor to the overall pool of primes.
Precisely. Each Fn has to be divisible by some prime. But since Fn and Fm, for n not equal to m, don't share prime factors, the prime dividing Fn must be different from the prime dividing Fm. An infinite sequence generating unique primes means
an infinite number of primes.
Yeah.
Got it. Okay, so the elegance lies in proving that relative primality thing for Fermat numbers. How's that done?
The source mentions a neat little identity. The product of the first n Fermat numbers, like F0 times F1 up to Fn1, actually equals Fn minus 2.
If Fn1 equals Fn2.
Okay, so suppose some prime p divides both Fk and Fn where k is less than n.
Right.
Since p divides Fk, it must divide that whole product F sin u F1.
Because Fnk is one of the terms in the product.
Yeah, so p divides Fn2, but we started by assuming p also divides Fn.
So if it divides Fn and it divides Fn2, it must divide their difference.
Exactly. It must divide Fn2, which is just...
So the only possible prime divisor they could share is 2.
But hang on, look at the definition again. Fn equals 2 to n plus 1.
2 to a power plus 1. That's always going to be odd, right?
Yeah.
For n greater than or equal to 0, 3, 5, 17, 257, they're all odd.
They're all odd, so 2 cannot be a common divisor.
Which means the only common divisor left is 1. They must be relatively prime.
Bingo.
Wow. Okay, that does feel like a book proof. Using this specific sequence, this little algebraic trick, it feels very neat, very focused to prove such a huge result. The insight is leveraging that structure.
It really is. Okay, let's stick with primes but connect them to something else. Sums of squares.
Fermat's theorem on sums of 2 squares. Which primes can you write as x squared plus y squared? Like 5 is 1 squared plus 2 squared, 13 is 2 squared plus 3 squared.
But primes like 3 or 7 or 11, you just can't do it.
Right, and the theorem nails it down. A prime pre works if and only if p is 2, or p is of the form 4 meters plus 1. Primes like 4 meter plus 3 are out.
Exactly. So 5 is 41 plus 1, 13 is 43 plus 1, 17 is 44 plus 1. They all work. But 3 is 40 plus 3, 7 is 41 plus 3, 11 is 42 plus 3. They don't.
How does the book proof tackle this one? It feels like geometry meeting number theory.
One of the key insights highlighted in the source is to translate this problem into modular arithmetic. It boils down to showing that the equation x squared is congruent to modulo 1 modulo.
X is 1 mod p, meaning p divides x off plus 1.
Right, showing that this equation has a solution if and only if p is 2 or p is of the form 4 meter plus 1.
Okay, but how does having a solution to xr modulo 1 mod tell you that PRs can be written as a sum of 2 squares? That feels like a leap.
It is a bit of a leap, but it's a known one in number theory, specifically from the theory of quadratic forms. Thew's lemma or Minkowski's theorem can bridge this gap. Essentially, for a prime p, if it divides some sum of two relatively prime squares, like x soft plus 1 bis, then p must itself be a sum of two squares. So the existence of that x is the crucial first step.
Ah, okay, so the book proof focuses on proving that existence, showing x lie 1, mod p, has a solution exactly when p is 2 or 4 meters plus 1. How's that done?
The source mentions a couple of elegant ways. One involves counting arguments about squares and non-squares modulo P. Wilson's theorem can be involved. Another uses the pigeonhole principle in a really clever way.
Pigeonhole principle.
How? You look at pairs of integers in a certain range related to the square root of P. There are slightly more than P such pairs. You use these pairs to define values x, y, mod P. Since there are more pairs than possible values mod P, two pairs must map to the same value. This collision, after some algebra, lets you construct the x such that x souchevé x1 mod p, but only if p is of the form 4 meter plus 1.
Using a counting argument on grid points to solve an algebraic congruence about primes.
Yeah.
Yeah, that feels completely unexpected. That's the book move right there.
It really connects different ideas beautifully. And relatedly, the source also mentions a nice Euclid-style proof just for showing there are infinitely many primes of the form 4 meter plus 3.
Which complements the 4 meter plus 1 case.
Nice. Okay, let's switch gears. How about that sum? The one that adds up to something totally unexpected involving pi. Ugh, the Basel problem. Summing the reciprocals of the squares. 1 plus 14 plus 19 plus 116 plus 1 forever.
And the answer is pi squared over 6.
Pi 6.
Pi 6. This is also the value of the Riemann zeta function at S2, S2?
That's just wild. Pi comes from circles, from geometry. This sum is purely about integers. How does pi even get in there? That connection seems almost magical.
It's deeply counterintuitive, and that's why proofs for this are definitely book-worthy. The source notes that S is known to be irrational for all even integers amount 2. So pi 6 isn't just surprising, it's irrational.
Its nature is surprising too. But so what's the book proof? Is there just one?
Well, that's the interesting thing. The source actually highlights multiple elegant proofs. There isn't just one path. One uses a clever double integral related to geometric series.
Okay.
Another uses a different double integral, but with a coordinate transformation, a completely different approach.
Wow.
And yet another one uses calculus, specifically the infinite product or series expansion for the sine or cotangent function, relating its roots to the integers. So multiple book proofs exist for the same result, each finding a different surprising connection, integrals, trig functions, polynomial roots, all leading to first 6.
Exactly. It shows the richness of mathematics. There can be many beautiful ways to see the same truth. And the source also gives a nod to Apéry's theorem from the 70s, proving it is irrational. That was a huge surprise too, and much harder.
Okay, from surprising sums to unintuitive geometry. Munsky's theorem. This sounds deceptively simple.
It really does. Munsky's theorem, you cannot cut a square into an odd number of triangles that all have the same area.
Wait, an odd number? Why odd? Equal area seems like the main constraint. Cutting a square into, say, 2 equal area triangles is easy. Or 4. Or any even number.
Exactly. That's the kicker. It has to be an odd number that's forbidden. It feels like it shouldn't matter, but it does. And proving this simple-sounding statement, well, it requires some pretty advanced machinery.
And the book proof mentioned in the source uses, what was it? A 3-coloring and something called the non-Archimedean valuation. That sounds intense.
Yeah.
How does coloring in some weird way of measuring size prove this?
This is where the book insight is really stunning, though maybe less intuitive at first glance. The proof assigns a sort of value or size to coordinates using a specific two-adic valuation, a way of measuring numbers based on powers of 2.
Okay, so points get a value based on their coordinates and this two-adic thing.
Right. Then you color the points in the plane, say black, gray, white, based on these values. The coloring and the valuation are ingeniously set up so that any line segment connecting points of different colors has a certain property. More importantly, it turns out that any triangle whose vertices have all 3 different colors, a rainbow triangle you could call it, must have an area whose two-adic valuation falls into a certain category.
Okay, and the square itself?
The area of the unit square is 1, and if you divide it into n equal triangles, each has area 1n. If n is odd, the two-adic valuation of the area 1n falls into a different category than the areas of the rainbow triangles.
Ah, So the proof shows that if you did have an odd number of equal area triangles, using geometric and combinatorial arguments about the coloring, you can prove that at least one of those triangles must be a rainbow triangle.
Exactly. But the area of that rainbow triangle, 1n, has the wrong 2-adic valuation, according to the theorem about rainbow triangles. It leads to a contradiction.
So you need an odd number of triangles to force a rainbow triangle via parity arguments. But the required area, one odd number, doesn't fit the valuation rules for rainbow triangles. That's incredibly subtle. Using number theory, valuation via geometry, coloring, to prove a geometric impossibility, definitely book-worthy.
It's a real masterpiece of connecting fields. Okay, let's stay with geometry, but add a combinatorial twist. The art gallery theorem.
The museum guarding problem. You have a polygon, like the floor plan of a gallery, with end corners or walls. How many guards do you need? Minimum, to see the whole interior.
And the beautiful result is, you need at most the floor of n divided by 3 guards, n 3, 4.
So for a 12-sided gallery, 4 guards are always enough. For 13 or 14 sides, you still only need 4. That feels really efficient. What's the proof idea?
The core insight comes from graph theory and coloring again. Step 1. Triangulate the polygon. Cut it up into non-overlapping triangles using only diagonals connecting existing vertices. You can always do this for a simple polygon.
Okay, divide and conquer. If you can see every triangle, you see the whole gallery. Makes sense.
Step 2. Think of the vertices of the polygon as nodes in a graph. The edges are the sides of the polygon and the diagonals you added for the triangulation. This graph is planar. Now you 3-color the vertices.
Assign one of 3 colors, say red, green, blue, to each vertex so that no 2 connected vertices have the same color. Why 3?
Because you can always 3-color the vertices of a triangulated polygon. And here's the crucial insight. Every single triangle in that triangulation must have 1 vertex of each color.
Why is that?
Well, imagine a triangle had only 2 colors, say red and green vertices. The 3 vertices of a triangle are all connected to each other. You'd have connected vertices of the same color, which violates the coloring rule. So it's impossible. Every triangle must use all 3 colors.
So every triangle has a red vertex, a green vertex, and a blue vertex.
Correct. Now, count how many vertices you have of each color. Let's say NR red, N green, N blue. The total number of vertices is NR plus NB.
Right.
By the pigeonhole principle again, at least one of these counts must be less than or equal to N3.
Right.
The smallest group can't be larger than the average.
Yeah, the smallest number has to be at most N3.
So you pick the color that appears the least number of times, say it's blue, and NB and N3. Now, place guards only at the blue vertices.
And since every triangle has a blue vertex.
Every triangle is watched by a guard. And you've used at most N3 guards. Done.
That is slick. Triangulate, 3-color, pick the smallest color class. Beautiful use of graph coloring for a geometric problem. Definitely feels like the book.
It really does. And the source adds a fascinating little twist. This triangulation trick works great in 2D, but you can't always partition a 3D polyhedron into tetrahedra without adding new vertices inside. Schoenhardt's polyhedron is the classic counterexample.
Whoa, so the intuition doesn't just jump to 3D easily. Interesting boundary.
Let's dive deeper into graphs now. They often lead to very visual combinatorial proofs.
Like the 4-color theorem for maps, though wasn't its proof famously controversial because it needed computers?
Exactly. Massive proof, computer-assisted. The source acknowledges that, but then pivots to a related idea. List coloring.
List coloring, how's that different?
Instead of having a pool of, say, 4 colors available for every vertex in list coloring, each vertex comes with its own list of permissible colors. You have to pick a color for each vertex from its specific list, still ensuring neighbors get different colors.
Okay, so it's a more constrained version. Vertex A might only allow red or blue, while its neighbor vertex B might allow blue, green, or yellow.
Right. Now, for planar graphs you can draw flat without edges crossing. It's fairly easy to show that if every vertex has a list of 6 colors, you can always find a valid list coloring.
Okay, 6 seems safe.
But the really neat book result here is Thomason's theorem. 5 colors in each list are sufficient.
Wow. Even with those individual restrictions, 5 is always enough for any planar graph. That's strong.
It is.
Yeah.
And the source emphasizes that Thomason's proof is considered brilliant because it uses a very clever, sophisticated induction. It actually proves something slightly stronger during the inductive step, which makes the whole argument work beautifully. It's not just about plugging into Euler's formula.
That's a classic proof technique, isn't it? Proving something stronger makes the induction hypothesis more powerful. Finding that something stronger is the art.
Absolutely. That's the book insight there. And the source also mentions that 4 list colors are not always enough. Voigt found a counterexample, so 5 is the exact bound.
Cool. Okay. From coloring, what about the friendship theorem? Sounds less intimidating.
It has a charming statement. If you have a group of people where every pair of individuals has exactly one friend in common,
Okay, me and you have exactly one mutual friend. You and someone else have exactly one mutual friend. Every single pair.
has exactly one mutual friend. If that condition holds for the entire group, then the theorem says there must be one person in the group who is friends with everybody else.
A universal friend. A central hub.
Precisely. The politician character, sometimes called. In graph terms, if every pair of vertices has exactly one common neighbor, there must be a vertex connected to all other vertices.
That structure seems very specific. How do you prove it always emerges?
The proof highlighted in the source by Erdős, Rényi, and Soos is celebrated for beautifully blending combinatorics with linear algebra.
Linear algebra. For friendships. How?
You represent the friendship network as an adjacency matrix A, where A is 1 if I and J are friends, 0 otherwise. The condition, every pair has exactly one common friend, translates into a very specific equation involving this matrix A, specifically A squared.
Okay.
By analyzing the properties of this matrix equation, particularly looking at its eigenvalues and eigenvectors using linear algebra techniques, you can rigorously deduce that the graph must have this central politician vertex.
Whoa. Using matrix eigenvalues to deduce the structure of a social network. That's completely unexpected. The book insight is bridging that gap between the combinatorial setup and the algebraic machinery.
It's a fantastic example. It makes you wonder what other combinatorial problems might unlock if we found the right algebraic lens.
Definitely. Okay, let's tackle Ramsey numbers. This is about finding guaranteed order within chaos, right?
Yep, exactly. Ramsey theory in general deals with finding inevitable structure in large enough systems. The number Rm, Mn, is the smallest number of people you need at a party to guarantee that there's either a group of M people who all know each other, a clique, or a group of N people who are all mutual strangers, an independent set.
The classic example is R33 equals 6.
Yeah.
In any group of 6 people, there must be 3 who are mutual friends or 3 who are mutual strangers.
Right. Finding the exact values of Rmn gets incredibly hard very quickly, but the source highlights a key result about a lower bound. Rk is at least 2 to the power of k2.
So you need exponentially many people to guarantee finding a clique or independent set of size k.
Yes. But the reason this proof is considered book-worthy is the technique Erdős used, the probabilistic method.
This is where you prove something exists without actually finding it, just by using probability.
Precisely. That's the revolutionary insight. Instead of trying to construct a huge graph that carefully avoids having a k-clique or a k-independent set, Erdős did something different. He said, imagine building a graph randomly. Just flip a coin for every possible edge. Heads, put the edge in. Tails, leave it out.
Okay, a totally random graph.
Now, calculate the probability that this random graph happens to contain a k-clique or a k-independent set. If you choose the number of vertices carefully around 2p2, you can show that the probability of finding such a structure is less than 1.
Wait, if the probability of the bad thing happening, finding the structure, is less than 100%.
Then there must exist at least one graph of that size where the bad thing doesn't happen, meaning there must exist a graph of that size that has no k-clique and no k-independent set.
So you've proven such graphs exist just by calculating probabilities without ever having to build one.
Exactly. It's a non-constructive existence proof. Mind-bendingly clever, incredibly powerful, and a signature example of Erdős' genius. Absolutely book material.
That's amazing. Okay, shifting from graphs to sets and counting. Sperner's theorem.
Sperner's theorem deals with antichains. An antichain is a family of subsets of some set, with the property that no set in the family is a subset of another set in the family.
So if 1, 2 is in my family, then 1 cannot be and 1, 2, 3 cannot be. They're all incomparable in terms of inclusion.
Exactly. Sperner's theorem tells you the size of the largest possible antichain you can form from a set with n elements.
And the answer is?
It's the number of subsets that have size exactly floor n2, the middle layer in the subset lattice. For a set with 4 elements, the biggest antichain consists of all the subsets with 2 elements. And there are 4 choose 2 equals 6 of them.
That feels intuitively right.
Yeah.
The sets in the middle are least likely to contain others or be contained by others. But how do you prove that's the maximum size?
The book proof highlighted, Lubell's proof, often called the LYM inequality proof, is just beautiful in its simplicity. It uses the idea of chains. A maximal chain is a sequence of nested subsets, starting with the empty set, adding one element at a time until you reach the full set, like 1 euro, 1, 2 euro, 1, 2, 3.
Okay.
The insight is to count pairs of chain set, where the set is in your anti-chain and also part of the chain. You count this in two different ways.
Double counting, a classic combinatorial technique.
Exactly. You relate the size of the anti-chain to the total number of chains and how many chains each set can possibly belong to. By comparing the counts, the inequality pops out, showing the anti-chain size is bounded by the size of the middle layer. It cleverly uses the structure of chains to constrain the size of anti-chains.
Using one structure chains to understand another anti-chains. Very elegant.
Now, sticking with sets, the book touches on the different sizes of infinity.
Countable versus uncountable. Hilbert's Hotel is the fun analogy for countable sets, right? Like integers or even rational numbers. You could always make room for more guests, even infinitely many.
Right, it helps grasp how countable infinity works. But the real bombshell is Cantor's proof that the real numbers are uncountable. They represent a fundamentally larger infinity. And the book proof is his famous diagonalization argument.
The proof by contradiction. Assume you can list all the real numbers.
Yes, assume you have a list, maybe just the reals between 0 and 1 written out with their decimal expansions.
List number 1, list number 2, and so on.
Now, construct a new real number. Look at the first decimal digit of the first number on your list. Pick a different digit. Look at the second decimal digit of the second number. Pick a different digit. Do this all the way down the diagonal of your imagined infinite list.
So the new number you're building differs from the first number in the first place, the second number in the second place, the third in the third.
Precisely. This new number you constructed cannot be anywhere on your original list because it differs from every single number on the list in at least one decimal place.
Which contradicts the assumption that your list was complete.
Exactly. It's a direct, powerful proof showing that the real numbers are inherently unlistable, a bigger infinity than the integers or rationals. The source even mentions the Kalkin-Wilf tree or sequence as a surprising way to explicitly list all positive rational numbers without repetition, really highlighting the contrast between countable rationals and uncountable reals.
Wow, a single sequence hitting every rational number. That itself feels like a neat book proof of countability.
It really does. Okay, for our last main category, let's look at some tiling proofs. Simple geometry, but with proofs using totally unexpected tools.
Like de Brugge's theorem about tiling rectangles.
That's the one. If you tile a big rectangle perfectly with smaller rectangles, and every one of the small rectangles has at least one side whose length is an integer,
then the big rectangle you started with must also have at least one side of integer length.
it sounds almost obvious, maybe, like the integer lengths have to line up somehow. But proving it rigorously for any possible tiling is not trivial. And the proofs, they come out of left field.
Okay, how does the book prove this? Not by trying to align edges, I bet.
Definitely not. One proof uses complex numbers and integration. Specifically, a double integral of the function e to the power of 2i times x plus y.
e2i x plus y. What does that have to do with integer side lengths?
Here's the incredibly clever insight. The integral of this specific function over any rectangle is exactly 0 if and only if at least one of the side lengths of that rectangle is an integer.
Whoa, so that function acts like a mathematical integer side detector when you integrate it over a rectangle.
Exactly. So you integrate this detector function over each small tile. Since every small tile has an integer side, its integral is 0.
Okay, sum of zeros is 0.
Right. The sum of the integrals over all the small tiles must equal the integral over the large rectangle because the tiles perfectly cover it. So the integral over the large rectangle must be 0.
And if the integral over the large rectangle is 0,
the detector property tells you the large rectangle must have at least one integer side length. QED.
Using a complex exponential integral as an integer length detector that is completely non-obvious and absolutely brilliant. A total book insight connecting analysis in complex numbers to basic geometry.
It's stunning. And there's another proof mentioned that uses a checkerboard coloring of the plane, but with tiny 12 by 12 squares, and assigns weights based on the coloring. The logic is similar. The total weight or value only adds up correctly if the large rectangle satisfies the integer side condition. Again, a totally unexpected tool.
Amazing. Okay, we've seen quite a range here. Primes, sums, geometry, graphs, sets, tilings.
We really have. So looking back, what makes these proofs feel book-worthy? What's the common thread?
Well, they almost always involve surprising connections, right?
Yeah.
Linking number theory to geometry or combinatorics to linear algebra or analysis to tiling, things you just wouldn't expect to be related.
That's definitely a key theme. And there's an elegance, a certain neatness or clarity. Once you see the core idea, even if the details are tricky, the central insight often feels disarmingly simple or clever.
Yeah, like the coloring argument for the art gallery, or using chains for Sperner's theorem or the probabilistic method. It's the power of finding just the right tool, sometimes from a completely different area of math.
That shows the power of different perspectives. Coloring, counting, probability, algebra, analysis, topology, all brought to bear on these problems.
It's not just about getting the answer, it's about the journey. Finding that beautiful, insightful path. The structure and logic itself becomes the thing of beauty.
Which brings us to maybe a final thought for you, the listener, to consider. We've seen how these proofs feel perfect because of their beauty, their surprising connections, their insight. It makes you wonder, why do we find certain mathematical arguments more beautiful than others?
Is that sense of elegance just something humans appreciate, like finding a clever shortcut? Or is the beauty somehow inherent in the mathematical truth itself? Does the perfect proof reveal something deeper about the structure of reality, or just about how our minds perceive patterns?
What does it mean for a proof to be beautiful, and is that beauty part of the mathematics or part of the mathematician? Something to ponder.